Welcome. In this video we will compute more examples of geodesics on the hyperbolic plane. So let's look at the following problem. Find equations of geodesics that connect 3 points, and the points are -2, 1, so that's the point A right here, -2, 1, 6, 1, so that's the point B, and 2, 3, that's the point C. And because none of these points are vertically aligned, I know that the geodesics connecting them will be arcs of circles whose centers are somewhere on the x-axis and circles that pass through any given pair of points. So let's maybe deal with AB first, just because it's very easy to find the center of the circle. So if I were to draw a line segment between these two and then find the midpoint and look at the perpendicular bisector and see where it intersects the x-axis, it's clear that it's going to be a 2, right? This point, 2 here, 2, 0, is clearly the point whose distance from A is equal to the point, is equal to the distance from B. Therefore, the circle that has this radius here, right, it's the same distance in both directions, will be the geodesics that connect A and B. We can actually compute this radius. So the Euclidean, so that's going to be the Euclidean distance between the point, let's say A, so -2, 1, and the center of the circle, so 2, 0, is, well, that's just the square root, right, of, you subtract the 2 minus -2 squared plus 1 minus 0 squared, so you get radical 17. So radical 17, that's slightly bigger than 4, so it's going to just pass it somewhere slightly north of the 4th marking here. So that is the geodesic, right? I could then get it sort of completed here, but the geodesic is just that arc. So what's the equation of the circle whose arc it is? So the center I have is 2, 0. So the geodesic, the equation of the circle whose arc in the upper half plane connects A and B, or is the geodesic between A and B, is the geodesic between A and B is, okay, so I have a circle that's centered at 2, 0, so that's going to be x minus 2 squared plus y squared is equal to radical 17 is the radius, so radius squared is 17. Okay, so that's the equation of that part. So now let's move on to the other points. So let me use a different color for that. So if I connect the points A and C, I'm gonna be looking for the point of intersection of a perpendicular bisector with the x-axis. Now you see that the midpoint, the points are -2, 1 and 2, 3. So the midpoint of the line segment joining them is here, 0, 2. And now I need to know the slope of this line, but it's 2 over 4, so the slope is 1/2. Therefore, the perpendicular line is going to have slope -2, so the perpendicular line goes like that. And if the line goes through 0, 2 and has slope -2, it's going to go through this point here, 1, 0. So that is going to be the center of the circle that is going to connect A and C. All I need to know is the radius, but that again is easy because I just compute the Euclidean distance. I'm going to leave this equation here. So this equation here was for AB. This was geodesic between A and B. So if I connect A and C, so what's the radius? So that I need the Euclidean distance between the center, which is 1, 0, and let's say A, which is -2, 1. So that is going to be the same thing as before, right? So 1 minus -2, that's 3. 3 squared is 9, plus 1, so radical 10. So I get the geodesic circle between A and C. Its equation is, so now the center is at 1, so it's x, maybe I'll just write it underneath here. So it's x minus 1 squared plus y squared is equal to 10. So that's the geodesic between A and C. So if I were to actually draw this circle, and I'm gonna, yeah, okay. So let's use the purple color. So the radius is just slightly bigger than 3, which means, yeah, I don't know what that means, but it's definitely, it goes like this. Well, I know what that means. That means that it's actually going to pass below the marking of 3 here, right? Because the distance of 3 to this point is already 3. So because the distance between the intersection of the circle with the y-axis 2, 1, 0 has to be 3, it has to pass below. Okay, and you already see how the picture completes here, right? So I need to do the same calculation on between the B and the C. So again, I'm joining these two by a straight line segment. It goes between 2, 3 and 6, 1. So the point in the middle is going to be exactly 4, 2. So again, the slope here is minus half, right? The run is -2. So the rise is -2 and the run is 4, so it's minus half. So the slope of the perpendicular line is going to be 2. So the center of the circle is going to be exactly here. So I can just draw then this last arc. The arc looks like this. And if I was now to write the equation of the circle, the center is at x. So it's at 3, 0. And the radius is the same as before. So this is the geodesic between B and C. Okay, so here we have the 3 geodesics. Of course, when I say geodesic between particular points, I mean an arc of that circle. I don't mean the entire circle. But one more comment about this picture. What we have actually drawn, these solid arcs, is a hyperbolic triangle, right? Because a triangle, well, I made a separate definition when we talked about the sphere, but the definition of a triangle will be the same for any geometry. Given you give yourself 3 points, and then you connect these points by geodesics, and you get a triangle. So that is geodesic, that is a geodesic, that is a geodesic. It looks odd, right? But for people who live on the hyperbolic plane, these lines, these curves here, they appear like straight lines. They are straight lines. They just sort of appear strangely for us because we're not looking at the real hyperbolic plane. We're looking only at a distorted planar representation of the hyperbolic plane. So here's one example of a triangle. This is not a vertex here, right? This is just one side, another side, and another side. Okay, let's do another example with a similar question. But let's change the points now. So this time the points will be 1, 1, 1, 5, and 5, 1. Okay, so let's draw that. One, 5, 1, 5. So the points are here 1, 1, that's A, 1, 5, that's B, and 5, 1, that is C. Okay, so in this case we already know that, well, we see that these 2 points are vertically aligned, so the geodesic between those 2 points is just going to be a Euclidean straight line. So the geodesic between these two here is going to be just a straight line. So let's just write this down here. Geodesic between A and B is x equal to 1, right? That's the equation of that straight line segment. What about the other ones? Well, here we face the same situation that we did last time with these 2 points aligned horizontally. So you already know that that's the geodesic between them is going to be a circle whose center is going to be here at 3. So it's going to, and the radius is going to be 2 squared, so 4 plus 1 squared, so 5, so radical 5. So it's, so radical 5 is slightly bigger than 2, so it's going to pass somewhat above this point here. And if we continued it down, it would intersect it. It would intersect the x-axis at a distance of radical 5 from 3. So the geodesic between A and C is the equation of the circle is going to be x minus 3 squared plus y squared is equal to 5. So finally we need to find the geodesic between B and C. So for this we connect them with a straight line. And we note that what's the slope of that line? Well, the rise is -4, the run is 4, so the slope is -1. So a perpendicular, so first of all, the midpoint is going to be exactly 3, 3. And the line that is perpendicular to this line segment that passes through 3, 3 will have slope 1, because that one has -1, right? So it's going to actually go through A and through the origin. It's actually going to go through the origin as well, right? If a line of slope 1 passes through 3, 3, then it's going to go through the origin. So that's going to be a circle that connects these two, whose center is at the origin. What's the radius? Well, that's just the distance of this point from the origin, so that's radical 18. Right? 9 squared plus 9 squared, that's radical 18, which is just 3 radical 2. Okay, so I'm sorry, that's wrong. This is not the radius, right? The radius is going to be the distance from the origin to one of these points. So the distance, the Euclidean distance between the origin and B is, well, the coordinates of B are 1 and 5, so it's just 1 squared plus 5 squared. So that's radical 26. Okay, so that's a circle that sort of starts here. Just slightly over 5, right? Because it's slightly over radical 25. And goes down here. Okay, so here this, so let's write down the equation, right? So geodesic between the geodesic between B and C is x squared plus y squared, because that's a circle centered at the origin, is equal to 26. So here's another hyperbolic triangle. The solid curves give you hyperbolic triangles. If you wish, you could now actually compute the angles. That is, so for example, if you wanted to compute this distance here, what is the, so the question, right? What is the length? So what is, so I'll erase this. This is now irrelevant for us. So let's actually compute some of the lengths. So from A to B, that's actually quite easy. So the hyperbolic length between A and B, that's just natural log of the ratios of the y values. So it's natural log of 5 divided by 1. So that's natural log of 5. Okay? So the length of this line segment is natural log of 5. Now, the other two are somewhat more complicated, because you need to look at the angles, and so this is something that you can use a calculator for. So because this circle here is centered at the origin, I just look at the angles from the origin. Okay, so here is angle alpha, and this one here is beta. So if I were to ask for the hyperbolic distance between B and C, that would be the natural log of the cosecant of beta minus cotangent beta divided by cosecant alpha minus cotangent alpha. Okay, but we know some things about these. That is, we know we can compute some other trigonometric functions for these angles, right? Because this point here, we know C is 5, 1. So I, for example, know that tangent of alpha is 1 over 5. So I already know cotangent alpha then. Cotangent alpha is equal to 5. And using trigonometric identities, you can compute cosecant. And then the same thing, you know, with beta, right? You also know the tangent beta. Tangent beta is equal to, so so B has coordinates 1, 5. So tangent beta is 5, which means cotangent beta is going to be 1/5. So we can also compute the cosecant, right? Because cosecant, so let's look at cosecant alpha, that's 1 over sine alpha. So we need to compute sine alpha, but sine alpha is going to be, so it's 1 over, what's sine alpha? So alpha is here. Sine alpha is this length, which is just 1, divided by the length of the hypotenuse, which is the radius of this triangle, so that of this the radius of the circle, the red circle, so that's radical 26. So I know that cosecant alpha is radical 26. Okay, and the same thing I can compute cosecant beta. So that's 1 over sine beta, which is 1 over So what do I get? What's sine beta? That's this length, which is 5, divided by radical 26. So I get radical 26 over 5. Okay, so I can actually compute this length. So with all this data, I know that the hyperbolic length between B and C is equal to natural log of, so I have cosecant beta radical 26 over 5 minus cotangent beta minus 1/5 divided by cosecant alpha, which is radical 26, minus cotangent alpha, so minus 5. Okay, so I hope that's all okay. So that's cosecant beta divided by minus cotangent beta divided by cosecant alpha minus cotangent alpha. Okay, so that's the hyperbolic distance between B and C. So that's the length of this arc here. This is the length of. Okay, so I'm not going to write that. That's the length of this side, the actual hyperbolic length of this side. Okay, and I wanted to finish this with one important observation that concerns points that are vertically aligned. So suppose we look at the following 2 points. So yx, so I take a point x1, y1, and then I take a point right above it, x1, y2. So I connect these 2 points by a geodesic, which is also a geodesic in the Euclidean sense, right? Straight line segments are geodesics in the Euclidean sense, and the vertical ones are also geodesics in the hyperbolic sense. So suppose I will, so let's call this point A and B, these points A and B. So suppose, so let C be the hyperbolic midpoint between A and B. So what does that mean? i.e. the hyperbolic distance from A to C is equal to the hyperbolic distance from B to C, and C lies on the line segment AB. Okay, so where will C be? First of all, remember that the vertical distances become larger as you move down, and they become smaller as you move up. So it's probably going to be somewhere closer to A than it is to B, in the Euclidean sense. So C will be x1. I'm just going to write it y0 here. And okay, so because of this equality, right? So we get, because of this equality, the distance between A and C, well, that's just the natural log of y2 divided by, between A and C. Sorry, the distance between A and C, that's just the natural log of y0 divided by y1. And the distance between B and C, that's just the natural log of y2 divided by y0. From which we get that y0 divided by y1 is equal to y2 divided by y0, i.e. y0 is the geometric mean between y1 and y2. That should actually remind you of something. y0 is the geometric mean between y1 and y2. In other words, y0 squared is equal to y1, y2. So let me just be led by a hunch and draw a circle whose center is down here, x1, 0, and whose radius is y0. So it's going to pass through C. Doesn't look nice. It does not have to go to the origin, just looks like this from a picture. So what is this? This is circle centered at x1, 0 of radius y0. What if I considered just a Euclidean inversion with respect to that point, so x1, 0, and radius y0. So that would be then the circle of that inversion. What happens to the point A under this inversion? Well, the image of the point A is going to be on the same line, because it has to be on the line that connects the center of the circle of inversion and that point. It's just a matter of how far it's going to be. But I know that, so if I call this A prime, I know that the distance from A to, and let's call this point, A, B, C, how about P, okay? Strange letter for the center of inversion, but let's do that. So I know that PA times PA prime has to be the radius, so has to be y0 squared. Okay? Fine, okay, but what's PA? That's just this distance, so that's y1. What's PA prime? Well, I don't know. That's sort of the question mark. Let's just write it as y1 prime, and that's supposed to be y0 squared. So from this, I get that y1 prime is equal to y0 squared divided by y1. Oh, but look at this. y0 squared divided by y1, that's y2. So B is the image of A under the inversion centered here of radius, which is the midpoint of the hyperbolic, which is the hyperbolic midpoint of this line segment.